So our next presenter is Andrea Latham, and she's going to be talking about micromilling technology. This is an issue that at ADOT we're dealing with. It's not as simple as it sounds. It actually can be a very complicated endeavor, and there's a lot of science behind it.
I am certainly thankful to be here today to talk about micromilling. It is such an exciting technology. We're seeing awesome case stories from all across the United States, saving municipalities tons of money. I've been working in and around the asphalt grinding industry for about 15 years. It's certainly, I'm happy to be here to share some of this with you. So today, during this presentation, I'm going to be going over the difference between milling, fine milling, and micromilling. We'll look at the different factors that dictate surface texture, the applications and advantages to micromilling, focus on one particular job story, and explore some new technology as well. There's three main types of asphalt milling: standard milling, fine milling, and micromilling. Micromilling very much similar to standard milling, except with an intent on leaving a much smoother surface. Here's a great comparison shot that kind of gives you an idea. The micromilling surface on the left, you can see how smooth and uniform that particular surface is versus the standard milling on the right. Some of the factors that dictate surface texture, there's 6 of them. Bit spacing, the forward cutting speed of the machine, the wrap configuration, so how many wraps are on the particular drum and how they're all working together, the drum RPM, the drum diameter, and cutter drum maintenance. The first one we'll check out is bit spacing. Here's an image of a standard milling drum. This would be referred to as a triple wrap 5/8 of an inch space drum. Triple wrap because there's 3 coils that wrap around that drum. 5/8 of an inch, you only actually see that when you get the interaction between all 3 of the bits, or all 3 of the wraps, I should say. The spacing between each bit on any given wrap is 1 7/8 inches. This kind of is a slide here that shows where the 5/8, the term of the 5/8 spacing comes from. And these are the 2 bits there that create that 5/8 of an inch space. Here's an image of fine mill drum, I should say, at 3/10 of an inch spacing, also triple wrap, so 3 coils, and it just has about twice as many bits as a standard mill drum. Something like this, you'd want to only use it in cutting depths of maybe just a few inches, 3, no more than 4 inches. Finally, a micro mill drum. This particular micro mill drum, also a triple wrap, 2/10 of an inch spacing. 2/10 of an inch only when you actually see the interaction of all 3 of those wraps coming around together. And each bit on any given wrap would be 1 inch or 6/10 of an inch. You have around 450 bits on this particular drum. It shows the spacing between the standard, the fine, and the micro, and kind of a perfect situation, with the drum coming around with the engagement of all 3 of the wraps. So you can kind of see the difference in the peak to the valley between all 3 and the spacing of the actual bits. Check out forward cutting speed and how it factors into the equation here. So in this image, this is great. It goes back to a 5/8 of an inch standard milling drum. And you can see that you only have the 5/8 of an inch spacing on the ground is actually just in this little tiny area there. From this pick to this pick right here, that's 1.25 inches, okay, 1.25 inches. And then you see 1 7/8 inches on is that showing on your end? So you'll see this section, kind of the larger section, you just see a little bit of the 5/8 of an inch. So you actually only see 5/8 between this little section. But that actually goes to show you when you factor in forward speed, what it actually does to that 5/8 of an inch space drum. And this is all the different factors would remain the same in this particular slide, except the forward speed doubles. So your RPMs, your wrap design, your bit spacing, everything's the same, except you see what happens in that pattern from 35 feet a minute to 70 feet a minute. It's a huge difference, and there's, 70 is an average, probably low side. They have a lot of high horsepower milling machines now that have 900 horsepower, and with the lighter the mills, the faster they can go. It's no surprise if they're milling, over 100 feet a minute at times. This is a nice field picture. Again, all variables the same, just a different forward cutting speed. This is your 5/8 of an inch standard milling drum at 90 feet a minute. So you actually only see that 1 7/8 inches on the ground there. We refer to this in the industry as veen out. That's when the cutter drum is just actually outrunning its cut. So now that we've kind of seen what forward cutting speed can do to a pattern, there's a bunch of different ways of minimizing this effect, and one is the wrap design. The industry started with a double wrap years ago in the late 70s, early 80s, and quickly moved to a triple wrap. So the double wrap just had 2 coils around that drum, whereas a triple wrap has 3. That third wrap allowed them to produce around 50% faster and still hold the same pattern. Shortly thereafter and presently, we're seeing a lot of interest in 4-wrap drums. And what's kind of interesting about the 4-wrap drum is you have a bit repeating. So with the double wraps and the triple wraps, you'd have one single bit that is in the cut on any particular line at any given time. The 4-wrap drums, you actually have 2. So that longitudinal ridge that you would see in some of those patterns that kind of would create that V mark, that second bit, that's 180 degrees, that kicks that ridge down. So you're holding a more consistent pattern than a triple wrap drum when you factor in forward cutting speed. Although the actual spacing per se, 15/16, or a lot of times you'll see 7/8 of an inch, is wider than a 5/8, it could be almost twice as smooth in the field. This is the side view of a drum of both a triple wrap and a quad wrap. Just this shows the degrees of the starts of the wraps. And then you see here the wrap design with the forward cutting speed the same, but the variations of the different wrap designs. So the 2 on the left side would be your standard drums, something that would be like an all-purpose drum, being able to mill 6, 7, 8 inches, no problem, 10, 12 inches even. 2 on the right would be your fine milling drum and your micro mill drum. And those are the ones that, of course, the spacing is much tighter, but you would want to keep those for just specialty jobs where the benefit of having that super smooth pattern would outweigh the cost of running it. Another great shot side by side just kind of shows that the tighter spacing does not necessarily mean you're going to have a smoother surface. The image on the left, 12 millimeter space drum, versus an 8 millimeter space drum on the right is cut at the same forward cutting speed. One is a double hit drum, so you have the one on the left, you have 2 bits on line, and the one on the right, you only have 1. So you can start to see that darker section kind of creating that longitudinal ridge, whereas on the left-hand side, that trailing tooth knocks down that ridge. And also, same thing, that an increased bit count does not necessarily mean a smoother surface. So the pattern on the right-hand side, 200, say on a 7-foot half lane machine, you'd have around 200 bits on a 4-wrap drum with that repeating tooth. And then you have 300 bits on the one on the fine mill drum that's on the left-hand side, but that just has that one single wrap, that one single bit that comes into play. So it's at the faster, at normal production speeds, that 4-wrap with the double hit really smooths things out, keeps everything more uniform. A lot of other benefits to it as well: smaller gradation of material sizing, less wear and tear on conveyor belts. The bits actually last longer because they're kind of splitting the load with the bit that's in front of it. So there's some other benefits as well. The remaining factors, RPMs, it's equally as important as forward cutting speed, but it's far less volatile. There are some certain, manufacturers of machines that allow you to change it. You can change shifts, you can change it on the fly. Maybe you could pick up another 20 or 30%, but it's not a massive difference. You also have the diameter of the drum that's always kind of set by the manufacturer of the machine. And last, but certainly not least, is cutter drum maintenance, because if you have all perfect factors, if you're not maintaining your cutter drum, you could be left with a surface like this. And I think to look at ways of preventing patterns, such as the last one, we need to always understand that equipment specifications don't ensure an end result, right? That performance-based specs, it does kind of give you, ensures an end result. It also allows you to change things up. If you have a different type of machine, different type of drum design, maybe you want to invest in diamond bits, maybe you want to increase your bit count another 40% because that would allow you to run 70% faster. So it kind of keeps that innovativeness in the system. Georgia, years ago, probably 10 years ago now, they were looking at saving money, and they said, okay, we have all these highways that have a surface course, an open graded friction course. And they said the underlying pavement was fine, but before they started a micro milling program, they would actually mill out 2 lifts of asphalt. And of course that's costly, especially when the intermediate structure was fine. But their thought was, okay, well, that open graded friction course, and that water needs to be able to drain through and get out. And if you just mill it up, and if you put that open graded friction course on a rough milled surface, that water would just get stuck in the grooves, right, of a standard milled surface. So they said if we could get a really smooth surface pattern, then that water would still be able to drain. So they used a laser road profilograph that would measure the peaks and the valleys of the grooves. And they would say, okay, you can't have more than 0.2 of an inch. And in some standard milling, fast speeds, you could see a 1/2 inch, 3/4 inch groove on that. So they came out with this spec, and it's just really, the state's had so much success with it, being able to actually just remove and replace what they need. So that was kind of the first performance-based spec that we really started to see for micromilling. Virginia, they have a nice sand test for fine milling. Their thought was the state was trying to save money, trying to disconnect the milling and the paving operation. Say, okay, before it was all mill and fill, but you know what? If we can leave a nice, smooth, safe surface for the motoring public, would you let us disconnect it so the milling crews can get a jump start on things, and then the pavers can come through, weather permitting, lay the mix, and so on. So that's what they did, and it's really worked out well. The state's saving a lot of money on construction costs by disconnecting 2 expensive operations, and the motoring public is safe. They have a nice smooth surface. And how the sand test works is there's a certain amount of volume of sand. Indiana uses a glass beads test for standard milling. Basically, it's a certain amount of sand or glass beads. You spread it on the surface. As long as the smoother the surface, the further it spreads out. And there's a way that you can read all of that, so you know what should be acceptable. Some things to consider. I was talking with a contractor in California, and they would starting to do also a lot of micro milling as well in front of thin lift overlays. And he said, look, performance specs can be tough though, especially in urban areas, because you have curbs and utilities, you have constant stop and goes, and you also, another thing is you always have to keep in mind the condition of the existing base course, right? Because if you have some failures when you remove that inch or inch and a half, you have to address those as well. So I think that when you're writing specs, you always have to be in consideration. We don't really know exactly what's under that surface course, and that things can change, and so you need to be flexible to a certain point as well. All sorts of different applications for micromilling. The 2 that we're going to focus on kind of today for this presentation is as a ride corrective tool before preservation treatments, and as a surface prep tool before preservation treatments. Micromilling in conjunction with pavement preservation, it really gives you the best of all worlds. You're able to go in and improve the rideability of roads, provide a better bonding surface, remove all the junk that's on the road so it adheres better, restore the curb line, reduction in material cost. You're no longer, when comparing to standard milling, you're no longer having to fill in a bunch of grooves. You're filling in 1/10 of an inch grooves, 2/10 of an inch grooves instead of a 1/2 inch grooves. Improves spread rate for your tack coats. Also, public perception. All of a sudden, you're riding on this road and it's smooth. People will notice, and also it's safety. If it's nice and smooth, if they're running on a milled surface, you minimize those concerns. In fact, there was a job I was kind of following in the city of San Jose. The contractor had just micro-milled, really a beautiful job, maybe removed an inch, inch and a quarter. They hadn't even put the thin lift overlay on it yet. And he said that people, pedestrians, on their bicycles were driving by their crew, giving them a thumbs up, because that's how smooth that road, just that micro milling. And he said, whoa, we haven't even put the surface course on. This is just running on a micro milled surface, how smooth the difference that can make on that. You'll see that reduction in construction cost if you can disconnect the paving and milling operation, or, hey, not look at reconstruction projects. Look at being able to improve rideability and address kind of these different jobs that before reconstruct you would think would maybe be the only way, mill and fill. All of a sudden, you're able to improve the ride and put a surface treatment on there as well. And it all comes down to enhancing, what's there, making it better. So the job story we'll focus on today is the Double Grove Street project in Los Angeles County. Awesome preservation program there in LA County. And it's the largest county in Los Angeles, or in California, I should say. 88 cities within the county, very diverse climate, 7,400 lane miles of road. The particular project is a Double Grove Street project, kind of what James said. They'll go in and they'll take full neighborhoods and they'll redo. So this particular project is the Double Grove project. Average age of the streets, 56 years old. Last slurry seal in 2002. Had some alligator asphalt, asphalt failure that they had to address. But when the county started looking at their options, they thought, okay, well, a thin lift overlay, that's not going to work, because they did have some underlying issues there. It was too rough. They needed improved smoothness. And a full reconstruction was just going to be too costly. So they came up with a hybrid approach by combining micromilling, doing a micromilling before the Cape Steel overlay. And this allowed them to improve the ride and to create a new riding surface. So there were 4 main components to the job: the asphalt patching and micromilling, the scrub seal, and then the wrap slurry seal. Okay, we have a video here. So as you can see, the County of Los Angeles, they do a fantastic job with not only implementing these preservation programs, but documenting them and sharing them on YouTube. As you can see, that particular project was a success. I mean, when you look at, a surface that comes out like this and you're able to save $1.4 million, it's impressive to say the least. Improved ride dramatically. It's just, to stretch those dollars, it's fantastic. So, and we're seeing this type of thing all over the country. I think it's just fabulous. The last bit we'll get into is some new technology. Going to be applied to milling machines, any sort of grinders. It's what we like to call flat tooth grinding. It's a radial system, so it's different than your standard conical milling bit. It's basically just for surface grinds. So conical bit's more of an impact as it strikes the surface. This is a shear effect, more like a planer. You get 100% surface coverage. It leaves a smooth and uniform pattern. There's no ridges on this particular system. Here's an image of a flat tooth drum. And here's a surface pattern. You can see there's no ridges there. So it's just taking a little bit extra mile. It's nothing that you would need to do before, say, a Cape Seal project or a thin lift overlay, but it's certainly something that's a great way of prepping the surface before seal coats. This is a nice surface texture comparison. Shows diamond grinding on the left and a milled surface on the right. Fantastic tool for pavement markings removal. In fact, we're seeing this all over the United States right now. With the flat surface, it just does a lot less damage to the surface as traditional conicals, or in this particular market, flail teeth, water blasting even. Here's a seal coat removal with the flat tooth. And only remove what's actually needed, and being able to do some sort of surface prep before these treatments. The flat tooth system can also be applied into different grinding attachments, milling machines. We put them across the board into all different variations of milling equipment. Great for doing surface grinds for new construction, for IRI improvement, maintenance work, dealing with frost heaves or expansion joints, pavement markings removal. This particular image is of Illinois DOT shaving off a frost heave that popped up. And it always amazes me. You get out there and it doesn't really look that bad, and then once you start grinding, it's, here you're grinding an inch and a quarter or so. Here's an example of that. This is in Belgium. It's about 2-inch grind, but you can also see how nice and smooth that surface is. Membranes and coatings removal, new pavement correction. What's nice about this, you can grind dry or just use water for just dust control. No waters, there's no slurry trucks or water trucks for diamond grinders. Milling for smoothness, in summary, it's great. There's the process, whether it be micro milling or flat tooth milling, it brings us so many different options. Roads that traditionally we would probably say, hey, look, no way, this is going to need a mill and fill, but it really opens up those jobs to preservation treatments, and therefore saving millions of dollars in certain cases and stretching those funds a little bit further. And in the end, you're going to end up with a better quality product, doing it before any surface treatment, really, to get that adhesion and everything else, the benefits that you see, not just the ride quality improvement aspect. At this point, I'd like to open up the floor to any questions. Okay, thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.